Okay. So so you can see that this is one type of CNN structure. So here the problem is there are three types of images. One is of horse, zebra, and dog. And then this input image will be passed through several filters or convolution layer, and then it will be flattened to a 1D array, and then it will be passed through a multi-layer perceptron. And this is here fully connected layer or multi-layer perceptron, and then we will use a softmax layer which will say which type of images is there. So you can see that the probability of being zebra is 0.7. So the classification will be this images is of zebra. So and the different and the significance of or the usage of using different type of filters or convolution layers are to learn several features of zebra. For example, you can see that in zebra there are several features like this black and white stripes, and then these legs, and then these eyes, muzzle, etc. So this convolution layer will learn these types of features of zebra, and then it will pass through the 1D array through the multi-layer perceptron, and then it will detect whether this image is of zebra, horse, and or dog. So this is the already discussed by Suraj, and now the problem is we want to classify the handwritten digit, which is called as MNIST dataset, and you can see that there are these types of images are there in this dataset. And for example, so you can see that in this whole CNN structure there are filters and there are multi-layer perceptron here. So the first type of code here is to just use this multi-layer perceptron. So you can see that in first line this MLP, actually in Keras this MNIST dataset is already there, so you don't have to download it, you just load it, and then you just see it which types of images are there. So you can see that this is the 20th uh, image in this data set, and you can print the shape of the data set. It means there are in training data set there are 60,000 training images of size 28 by 28, and in testing there are 10,000 images of 28 by 28. Now you can convert it to a matrix of 60,000 into 784, but just using this reshape function. And then if you just call the shape function, you will see that it just 60,000 into 784. So from 28 by 28 from 7 to 784, and then this code is doing just normalizing these pixel values to train faster, or to or to speed up the training. And then this code is for multi-layer perceptron. So you can see that there are only activation functions and there are no convolution layers or max pooling layers or any other filters. So you can see that there are in this network there are first 1024 activation functions which is of ReLU, and input size is 784 in first layer. So you can see that you can think like this, there are 1024 these types of neurons or activation functions are there, and each of one is of ReLU. And then we have used this tanh and then sigmoid like that. So you can see that in, and then after the ReLU there are 128 tanh functions, and then dropout is used to reduce the overfitting. So what it will do it, if this multi-layer perceptron is very large, then it will automatically kill or probabilistically kill some of the neurons such that the weights of this multi-layer perceptron is reduced. That is why this dropout layer is used here. And then 64 activation functions of ReLU, and then the softmax. And here it is 10 because in number there are 0 to 9, that is why 10 classes. And then you just run this model.compile. So here optimizer here used is Adam, and loss is categorical cross entropy, and which computes the categorical loss between the labels and the predictions. So you can see that after the softmax there will be some probability values, and in your test data in y test there will be some value like 1 2 3 4, and you have to first convert this array to a one hot encoding. So and it will be a array of 1D array, and then you can uh, compare, you can calculate the loss, and this loss is here is cross entropy loss, and then the accuracy matrix is accuracy. So now if you fit it for 10 epochs and batch size of 64, you will see that the accuracy after 10 epochs is 99%. So you can run the test accuracy here, and for prediction you can see whether the model is correctly classifying or not. So for example, for that, uh, this prediction is called here. So here the prediction, this object is loading some predicted values of 0 to 99. This predict and these predictions are actually loading this data. So you can see that. So if you just print seventh index in prediction, so in prediction there will be of 0 to 99 of size of array, and if you just print seventh, so you will see this kind of array, and this is and one in each of this element is saying that probabilities of that input belongs to the given class. For example, this is for 0 1 2 3 like that. So from these probability values you can see that the maximum probability values for 9. So 0 1 2 3 4 like that 9. So here now we have used this argmax function to calculate the maximum probability over these arrays. So and it will say that this is of 9, and if you test it using test data you will also see that actually this is of 9, this image is of 9. And similarly we have seen for 4 also, and one example for wrong prediction. So you can see that someone is written this 3 like a 8, and this model is also misclassified it as it is saying that it is 8, but the actual level is 3. So this is one example of misclassified images. And now you can just plot that how many numbers of misclassified and correctly classified images are there. So this is the actually predicted values, and this is the actual values, and this is saying that whether this prediction is correct or not. For 7 and 7 it is true, like that some points are false, like that. And if you use CNN instead of multilayer perceptron, so you can see that in CNN also in between their last before softmax there is a multilayer perceptron. So the rest of the code is similar. So here just in CNN you have to use different type of filters depending upon the problem or depending upon the dataset you have used. So here the dataset is very small, that is why small numbers of filters or convolution layer is used. So you can see that first the dataset is loaded, and then accordingly it is just reshaped into 60,000 into 784, then normalized it, and then just use the one hot encoding, and then this is the structure of CNN or convolutional neural network. So you can see that in first there is a sequential, and then this is a filter con 2D filter, and the size of the kernel is 5 into 5 of, and number of kernels is 32, input size is this, and activation is ReLU. So this is different types of kernels, and then max pooling, which is already discussed by Suraj. So the significance of using this is actually these max pooling layers are used to reduce the dimensions of the feature maps, or to locate to implement the location invariant feature in your model. And then this dropout is used to reduce the overfitting, and this flattening is for this type before this. So before feeding this whole result after convolution, you have to flatten into 1D array, and then you have to feed into multilayer perceptron. So this is the flatten layer here in this code. Flatten, and then this is the dense. So this is a multilayer perceptron again, dense 128 such activation functions are there of ReLU, and then softmax is there. So softmax will say that this image is belonging to class 9 of probability of 0.9, like that. And then the loss function is categorical cross entropy, and optimizer is Adam, and rest is similar. And then you just fit it for like 10 epochs, and you will see the accuracy is 98%. So this is the CNN code, simple for MNIST dataset. But for different types of images, if the images is complex in nature, then you have to use different types of convolution layer or max pooling layer. And here are the some applications of CNN application. For example, in natural language processing, CNN is used, for example, in search query retrieval, sentence modeling, text classification, and prediction of next word, like that. And in AI based games, CNN are used, for example, to predict the next move in checkers game or AlphaGo, etc. And CNN is also heavily used in this field, image recognition or analysis, for example, facial recognition, medical image analysis, etc. And video analysis, for example, human activity recognition. And also in bioinformatics or drug discovery, these types of CNN are also used, for example, drug property prediction, bioactivity or small molecules prediction, etc. So that's it, I think, for CNN. So now you have any question, so you can ask.
Hello,
Yes.
sir. What is hot encoding? Like, what is the role of that?
So one hot encoding, what it is doing is, so it will just put the uh, it it will transform to a 1D array. So you can see that, for example, uh, we have used one hot in this line. So y equal to 2 categorical y train. So in y train, there are several types of images are there. So one hot encoding, it will do, you can see that after using this one hot encoding, the array size is reduced to 60,000 into 10. So it will just take the whole matrix and it will convert to a 10D 1D array of size 10. So there are 10 types of actually 0 to 9, there are 10 digits, 0 1 2 3 4 5 6 7 8 9. So each image now will be represented as a 1D array of size 10. That is the meaning of one hot encoding. So you can think like this. This is a one hot encoding. Actually, this is for flatten, but you can also think after using this one hot encoding, the whole array or this whole image will be converted to this type 1D type of array of size 10. So 1 2 3 4, like that. There will be 10 cells or 10 um, indexes 0 to 9, and the array size will be 1D array. So that is the thing one hot encoding is doing.
So, in perceptron algorithm, we use the same, like we use this thing, and in case of the convolution 2D, we use the flatten. Like both have similar role.
No. Actually, flatten is also used in this. You can also use this also, and CNN also this. Actually, this here one hot encoding is used to just calculate this loss, this categorical cos entropy loss. So how much loss is there? But this flatten is all actually in convol. If you use just multilayer perceptron, then you don't have to use it. But you have to, if you use CNN, then first you have to take the whole matrix, because any type of matrix you take, it will be of matrix RGB, or any type of grayscale image, it will be a matrix. Then on that you have to first use this different types of layers, and after applying different types of filters or convolution layer, the output also will be of small size of a matrix. And then this matrix will be converted to a flattened layer, and this flattened layer has nothing to do with this one hot encoding. So you can think this one hot encoding vector is used here and flatten is used here. So why here you can see that this white train is this, where is this? So white train is one hot encoded, So here it will be, and the loss will be predicted after this multi-layer perceptron after this layer. So one hot encoded is done for that purpose, but flatten is done before to fade into the multi-layer perceptron. Because you can't just fade a matrix into a multi-layer perceptron. So to fade the whole uh, resultant matrix after different types of max pooling or convolution layer, you get the matrix, then flatten it to a 1D array such that in your RAM it can fit it, and then to fade into a multi-layer perceptron to classify it, that whether this type of images of 1 2 3 or zebra or cow, like that. So you have to flatten it. Is it clear?
Yes, sir, got it. Yes.
Okay. Okay, then the next part will be presented by Sujoy sir. Thank you.